For you, I have 21 shading tips you probably don't know. And if you ask nicely, then I will tell them to you. Okay, you had me beat. Let me tell you them.
My camera died for... I'm kidding. It's a joke. The video is high quality even though the intro was low.
These shading tips are sponsored by Brilliant, but we are going to talk about that later. So the first one has to do with how I got this gradient on like the how I. If I take a color ramp, I basically want to sample the colors being the yellow, the red, the black, whatever. We know that we can hover and hit E for eyedropper and then, sample yellow, go to the next one, sample black. Well, did you know if you hover over this and hit E, you can click and drag and get a whole bunch of colors in the order that you did. Let's get a gradient texture going here. 0 to 1, 1 to 0, and you have it perfectly. Thank you, Hale. For the next one, I want you to assume you have rebar, or basically an object that needs rust, and you haven't UV mapped it, and you don't want to. Let's take an image like this that is very obviously not seamless. And this is what it looks like. Right now, it's using a UV map, and it looks hideous. Did you know you can change flat to box projection, which will mess up your model, but then take your coordinates and change them? I'm going to do generated coordinates, and all of a sudden, we have a free unmapping, or I guess unwrapping, and for where we have these seams, you can increase the blend factor, and then all of a sudden, your seams are gone, and then you can rotate it, and it just works. So easy texture mapping without any trouble. Now for this trick, suppose you have modeled a room or basically something in a window and you don't want to show it from a different perspective. Here is how you do that. I'm going to focus on the material of this object and we are going to add in literally a geometry node. And in here, you're going to see something called back facing. The way this works is it's going to be black in one orientation. And then if you go to the other side of the face, it's going to be white. Maybe a better way to show this is let me give this a material. You can see it changes depending on the side. And if I was to flip normals, then that is going to invert. Take a principled BSDF and I'm going to take a holdout shader, which is going to hide things, and I'm going to mix these together by this back-facing factor, which assuming you have the order correct, will do this, and then it will hide it. It's basically a way to compress space into like a flat plane. Now, suppose you want to make kind of like a noise texture that looks like circuit board. Here is a trick. I'm going to start off with a noise texture, which looks nothing like a circuit board, but the trick is I'm going to manipulate these coordinates to kind of force its hand. I'm going to use a Voronoi texture. I'm going to put the distance in here, which creates these circles. That's no coincidence because you see these kinds of dots. I change Euclidean to something like Manhattan, and then all of a sudden we get something more like squares, and then we're almost there. I just need to take this and bump up the contrast. So kind of use a color ramp here to define these nice lines, and I can change the scaling of this to kind of say, here's the density of my circuit board, and I can have a uniform distribution for a carpet or something like this, and then as I bring up the scale, it's looking very circuit board-esque. White is going to be mapped to kind of this green color, black can be black, connect that to the principled BSDF, use a tiny bit of bump mapping, and just like that, we get this nice kind of circuit board material that you can push a bit further. Speaking of Voronoi, did you know you can kind of make a stained glass pattern out of it? I'm saying we can take a kind of piece of data, we already have like a image texture, let's use this rust thing. You're going to take the position, you're going to put it in here, you're going to see it's going to keep the color palette. For now, you can kind of choose what kind of stained glass you want out of this, and then as I bring up the scale, you're going to see at a high density, it's going to kind of recreate this image, but at a quantized kind of stained glass kind of look. And this is a good way to get some like NPR stylized shading. So here I have a half-assed attempt at like hard surface modeling, and when you render this, the kinds of things that make it look good is every single sharp edge should receive a tiny bit of bevel so it catches some light. So if I give this kind of like a shiny metallic material, you're going to see these edges are very harsh, and instead of like beveling every single piece, which yeah, we can do with a modifier, there's a trick to get bevels for free without ever modeling them or adding geometry, and the answer for that is this bevel node. What you need to know about the bevel node is it's kind of like the normal map, but it's slightly blurred. As you can tell, it's slightly blurred. What this means is if you use this as your normal coordinates, all of a sudden you get these bevels for free. So without and with, as you make the radius a bit tinier, it's going to look better and better. As I model, it's going to add in those bevels, even for things that themselves have bevels. So because this is just kind of like a blurred version of normals, it would make sense to kind of calculate the distance or the difference between them. So I'm going to look at the distance between the normal and the bevel, and you can see all of a sudden it did a pretty good job at extracting a edge map. What this means is I can have one principled BSDF here, another one here, mix them together using this distance, where maybe this one is kind of like a grungy dark kind of color. And if I take this distance map and basically increase the contrast and then swap that out with the factor, you can see I've isolated these edges, which you can almost use as a wireframe modifier. We'll talk about it, but you can see it's nice and dynamic. Kind of in the same vein, if we can isolate edges, which is good for edge wear, I also want to isolate like concavity, areas like this where dust would accumulate, etc. First of all, a bit of theory. If you go to render passes and you go to ambient occlusion, you can see this kind of gives us what we want, where it's black black and areas of concavity. That's what we want to emulate. And it turns out there is a node for this. It's called Ambient Occlusion, which will basically give us our Ambient Occlusion render pass, take the color ramp, make it higher contrast, and now we have a concavity map, which I think right now I have them inverted, so I'm just going to flip them. And you can see this way I've isolated areas of concavity where you might want dust or dirt or whatever to accumulate. Of course, what you would do with this is you would take it and maybe multiply it with a certain source of randomness, like maybe a noise texture or something like that. And I'm just going to do a few inversions so that this makes more sense. And now you can see I've isolated concavity areas, but with this nice kind of noise pattern. So this is without, and then this is with. Just two ways to kind of destroy your model. There has been a lot of vector math so far, and you better believe I'm about to talk about more. And if this is kind of like, what is going on? Well, I have a solution for you with the sponsor of this video, Brilliant. This is an online platform dedicated to teaching you skills like this and things related, things like math, programming, AI, stuff like that. They kind of take an approach that isn't just like read, answer questions, but they have a lot of visual and interactive kinds of ways of learning. And specifically for this video, I would recommend looking into vectors, things like vector decomposition, adding, subtracting, dot product. You want to understand what is going on, and now you can. So what you are going to see below me, somewhere here, is a link on top of a QR code somewhere, which when you click will not only give you like a 30-day free trial of Brilliant, but it will also give you a 20% discount on the actual annual membership. So this is a great way to get started. And now we need to talk about more tips, I guess. And now one more trick of the trade with edge masking and concavity masking and all this is you might want directional masking. So what I mean is you want to isolate everything facing this direction or everything facing upwards if you want to put snow on the top of it, whatever. So what I'm going to do is I'm going to start off with your normal coordinates, which we can find here. This kind of shows which way things are facing, which of course updates as you rotate a normal node. I'm going to connect this here. And what we want to look at is this dot product, which you can see isolates a certain direction. And as I rotate this, we're getting different, directions here. Maybe this one can be like a glass BSDF or something weird like that. I use this as the mask. Yeah, here you can see it's isolating certain directions of it. The thing is, it's not very intuitive to understand which way is facing what using this kind of weird interface. What I would recommend is we can calculate this dot product ourselves. The way you do this is you take vector math. There is a dot product function somewhere. And all you need to know is if I want the kind of faces pointing upwards, in other words, up on the z-axis, I compare this to 0, 0, 1, and then we get that. If I want the x-axis, I do 1, 0, 0, and now we're getting things that face the x-axis, etc. Now we're going to tackle a notorious problem in shading, which everybody says you can't take a image texture and blur it unless you take it to Photoshop, blur it, and then bring it back. Well, this is true, but not exactly. Because if you look at the coordinates that this image is using, it's using UV coordinates. Of course, I can manipulate those and that will change what we see. But instead of just like moving this left and right or up and down, what if for every single point we move it in a random direction? So this one goes here, etc. We should expect this to kind of look blurred because it's sampling things in different directions. Turns out there's a nice way to do this with something called a white noise texture. You want to combine this with generated coordinates. It's going to be really hard to tell what's going on. It's going to look gray, but every single point is going to receive a different number. You're going to add this to your UV coordinates, which will really make it really strong and insane. So I'm going to take this and I'm going to scale it down such that when it's very tiny, you can see it does this blurring, but it also kind of shifts it down to the side. The reason for this is white noise is a number between 0 and 1, which means on average it's going to shift it by 0.5. To compensate for that, I'm just going to subtract by 0.5, so this is centered at 0. And now you can see we have a blurring node. Speaking of blurring, can we actually simulate depth of field in shading? Well, let me show you what I mean. I look through the camera, and I'm just going to look at pieces that are kind of close to this. And for now, let me turn off the blurring. I'm going to turn on depth of field. I'm going to make it really, really tiny, and then kind of set the focal distance. You can see this basically creates a depth of field effect, which you can think of as taking this texture and blurring it as you go in this direction. So you're probably seeing where I'm going with this. And before we do that, we need to know where our camera is if we want to look at the distance from the camera. So how do we calculate that? Well, there's two quantities that are useful for this. First of all, we have our geometry node, which has something called incoming. What you're going to see is as I change this, it's going to change kind of the color of this. It almost looks like there's something beneath it. And the way you want to think about incoming is we have a camera facing a shading point. It's going to look in a certain direction at this shading point, and I believe the incoming actually calculates the inverse, so it's going to show kind of the shading point to the camera if we know the position of the point. So let's take a point over here, which has some position relative to the origin. I take this and then I add this incoming, the one that's facing this camera. Well, those two things added are going to give me the camera position for every single point, in the shading plane. So if I take this position, which changes depending on where it is, I'm going to add the incoming, which is almost correct, but notice that that different points are going to be different distances from this camera. So this one's kind of close relative to this one over here. This incoming is always of a magnitude 1, so it only tells you the direction. Well, we have a node for that. It is called the camera data node, which tells you exactly this information. We can look at the view Z depth and the view distance. One of them, this one, is kind of the distance, and this one is the distance of each pixel. So here, I just kind of map range this. You can see as I get further away, the distance gets bigger, and as I get closer, it kind of gets darker. So I'm going to take these, and I'm going to scale this incoming. I'm going to scale it by, let's say, the Z depth. And now the magic of this is it's going to be a single color, which makes sense because as I change this, the camera only has a single position for every shading point. So if I look from above, this should be pretty blue because I'm only on the Z axis, which is blue. If I look from the X axis, it's going to be quite red. If I look from the Y axis, it's going to be quite green. And now we're going to be ready for depth of field. So remember, we already had a setup for blurring. It took this image, and then depending on the scale of our white noise, it blurred it by a certain number. Well, what if we make this number kind of like the distance from the camera? Now, of course, you can kind of use this Z depth directly, which will work, but I just wanted to show you that we can literally extract the camera so we can do fancy effects. So you can kind of take the position of the camera and calculate the distance of the position to that camera. It's going to be quite big unless you get super up close. So again, I'm going to map range this. This is the equivalent of picking your focal point. So I'm just going to look for big distances versus small distances. So I'm going to scale our white noise by this quantity. And now you can see it kind of gets in focus. And as I move out, it gets out of focus. And you can do this with a entire scene, by the way, assuming you have a texture or something on it. This principle of like taking a coordinate system, so again, we're using UV coordinates by default, and then we're distorting it. This kind of principle of distortion works more than just with white noise. So let me show you what I mean. So for this one, let me use a noise texture. Very important, whatever coordinate system you're using for your image texture, just use the same one for your distortion so it lives in the same space. The way you mix these together is you can do what I did before, or even easier. You're going to add a mix color. You're going to set it to linear light, and then you are going to combine this here, which lets me kind of add this distortion with a single slider. You can think of linear light as basically doing that subtraction by 0.5, 0.5, 0.5 that I no longer explicitly need to put here. So as I bring up the detail on my noise, you can actually simulate kind of like this depth of field, but now it's a bit more stylized and painterly, and you can distort with something else. So let's do a Voronoi texture and then increase the factor. And this time it's going to distort, but with these kind of circles, and we know that we can change those to squares or whatever. What if I wanted to take our coordinate system and repeat it? Or actually, let's just use object coordinates for this, which looks like this. It's going to be centered in the middle. I'm going to calculate the distance from the center point, which it's going to be black over here, and then kind of increase. If it's looking a bit stretched, that's probably because I stretched it. You can just Control A, apply scale, and that'll fix it. I'm going to look at this distance where it is greater than or less than a certain number. You can think of this as a procedural way to make a circle. Fine. But what if I want to tile this and make a grid of circles, almost like I'm making an alpha for like a pencil holder that has all these like grates, or like a cheese grater or whatever? What you can do is you can take your object coordinates, and just like before, you can scale them, which is basically just going to scale the circle. But the trick is, after you scale it, you want to run it through another vector math. But for this one, you're going to set it to fraction. And what you're going to see is that this is going to tile it. So first of all, I had my object coordinates, then I scaled them, and then with fraction, I've literally repeated the coordinate space. In this case, we now want to center by 0.5. That's a unique case to this one. So I'm just going to center by 0.5. And then just kind of change this number over here. And now we have kind of this grading where with a single number, I can change the density of this and tile basically anything. I made a circle using a very simple function, and there are functions for doing circles, squares, other shapes. I just want to go over some of them here. I want a circle centered in the middle, something like that. And if I want that, I need to know the distance from the center point. Literally what I did is I calculated the distance from the center point, which will give this radial mass, or really it's called like a spherical mass, but whatever. And I said, where is this radius? Basically less than a certain number. And that is exactly a circle. But you could have done anything with this mask. You could have made a donut by just changing some of these numbers here, just using this radial mask for different things. So in this case, I'm comparing this radius to a certain number, and I'm saying where are these equal within some threshold. But I can do more complicated things. So for this object coordinates, I'm going to separate by x, y, z. I'm going to send this through a absolute value, so the negatives become positive. And now I basically have a mask telling me the distance from this midline relative to the x-axis. And then for the y-axis, we have the same thing, but inverted. I'm going to take these and I'm going to add them together, which you can see kind of makes this diamond, which is very familiar from the distance mask where it kind of made this circle, but this time it's a square. Take this and I check where the radius is greater than or less than some number, and now we have a square, which we can rotate it if you don't like its position. So you just vector rotate by 45 degrees. But this kind of brings a new idea where we can now put any distance metric here. In fact, the circle uses the Pythagorean theorem. So you're going to remember it is x squared plus y squared, and then you take a square root technically. But we can change this power to a different thing. So let's kind of make a value over here to kind of get this where I want it. I'm just going to do something to the square roots. Again, Pythagorean theorem, I'm sorry I keep saying this. You're going to see a lot of 2's because if I make this square root actually a power of a fraction, this is equivalent to taking the power of a half. That is what a square root is. And you're going to see this number 2 keeps appearing. So if I change this to the number 3, I also want to change the square root to be a power of a third. So instead of taking a square root, I'm going to change this to a power 1 over this number. And I guess the only thing is because this might be an odd number, I'm just going to take the absolute value of both of these. As I increase this, you're going to see we're converging on a square, but in between we get something called like a squircle, like a square circle. This is how you make this shape, or you can make a star using the same kind of principle. And it turns out if this star and square and circle look familiar, this is exactly what Voronoi texture does. So you have all of these circles because it's using the Pythagorean theorem. That's called the Euclidean metric. If I change this to the Manhattan metric, that's the taxicab metric. And if I do the Minkowski, you're going to see we have this exponent when we set it to do, we get these circles, and as we make it higher and higher and higher, there are these squares. Speaking of all the shapes we made, let me show you another trick. So if I take my cube and look at the texture coordinates, there's a lot that we've dealt with, right? Generated, normal, UV, object. There's this one nobody uses called parametric, which you're going to see seems to really look at the geometry of this and kind of respect it. In fact, what it's doing is it's taking this and kind of like tessellating it or triangulating it. And what parametric does is it takes each of these triangles and makes a coordinate system on it. This is called parametric coordinates or barycentric coordinates. So I can separate the x component to get interesting masks or the y. It's just nice to know these exist because we can do the same kind of tricks we've been doing where we calculate the distance. I'm going to take vector math, calculate the distance from the center point. It seems like it's something like a third, or something like that. Maybe that is the exact number. But you're going to see this lets us kind of center a dot on every single face. I take this and do the less than, and now I get a circle on every single face. So you can use this as kind of like a polka dot pattern that updates. There aren't many uses for this. I'll talk about like one use, but this does exist, I guess. You're going to note that we have a wireframe node. What it does is it gives us a wireframe of all our faces, even if we subdivide or whatever. But just like parametric coordinates, you're going to see it has this issue where it kind of triangulates it. If I have a quad over here, I don't want to show this diagonal. Well, parametric coordinates, even though it has these triangles, can help us with this solution. We're actually going to do a bit of a throwback here where we're going to bring back the bevel node because remember the bevel node kind of highlights these edges which are part of the wireframe. So I'm going to take my bevel and compare it to normal coordinates like we did last time, which almost gives us the wireframe, but it's missing these diagonals. Even though it's a quad, it has these diagonals, and this is where parametric coordinates come in. Remember, I can separate by the x or the y-axis. One of these is going to be more useful than the other. I'm going to take this x coordinate and see where it is less than a certain number. And you're going to see if I make this really tiny, it's going to give us certain lines. See where I'm going with this, right? If I take these and combine them with a addition, it will give us a wireframe node that actually doesn't triangulate things. So if I inset here, it's literally going to make the quads. And if I do happen to triangulate, so let's just triangulate this face, it will break. Okay, well, assuming yes, all quads, this is a wireframe modifier, kind of like a hacky wireframe modifier that works in most cases. I'm not gonna claim that it works in every case, but it seems pretty good. By the way, you're gonna see in some cases, it does keep the diagonal, but that is the result of this bevel. So if I take this this kind of like bevel coordinate and then just kind of clamp it to get rid of this, you're gonna see that's gonna get rid of these triangles. And now we do have a wireframe shader. There is a second trick to do this. In fact, I'm gonna take the texture coordinates, I'm gonna do something very weird and look at the UV coordinates, which right now look something like this. It has a default unwrap. If I wanna do a wireframe, basically for each face, I wanna say what is the distance from the edge? Well, if I was to take this and kind of do a kind of silly unwrap where I'm gonna go to edge mode and mark everything as a seam, and then I'm gonna do an unwrap, you're gonna see every single face is in its own island. If I now take this and run a reset, for every face that is a quad, you can think of this as basically like overlapping except for the triangles. And if I was now to highlight the edges in UV space, we expect this to look pretty similar to a wireframe. So just kind of like a simple way to do this is I can look at the X coordinate and I want to say give us the edges where it's very close to 0 or very close to 1. I'm going to compare this to a half, like the midpoint, and then I'm just going to increase this until it's like 0.49, which you can think of this as kind of like inverted. If I have 0.49, I care about a distance and UV space of like 0.01. So I'm going to do this on the X. I'm going to do this on the Y, which together are going to give us our full wireframe. So this one's inverted, and then we add them together. I want to do an addition in a single math node, not a vector math node. And this is going to approximate a wireframe shader. The benefit of this one is it seems to be much cleaner, but I don't think it handles triangles very well. The issue with a triangle is it has this diagonal, which isn't on any of the 4. But I think we're lucky here where this one compensates. I'm not sure. But here you can see we have a triangle edge missing. I am losing my voice, but where are we? Okay, we only have 5 tips to go. For example, let's say I have a subdivided cube and I want to isolate this face. Let's do it in solid mode. I want to isolate this face in particular, right? Not anything else. We know that if we hit Control G, we can assign this to a new vertex group. This makes a group right here. I'm going to call this first. If I go to edit mode and select, it's going to show us our selection. Let's do another face like this one, put that in a new group, and I'm going to call this second. In other words, we have 2 different groups or attributes that I care about. The key word of what I said is attribute, because there's a node that you might not know about called the attribute node. If you spell it correctly, then it will show up. Attribute node is very, very powerful. It connects with all different parts of Blender, which we're going to get to, but one of those parts is these vertex groups. So if I type in first and now look at this factor, you're going to see it almost gives us the right thing, but basically the issue is this is a vertex group on a, I mean, it's on vertices. It's not a face map. It's literally just telling us which vertices do we care about, meaning that a vertex like this one is activated, and because of interpolation, it's going to show things over here. But what if I wanted to isolate literally this face? For this face, we have the special property where every single vertex is lit up, right? That's not true with any of these other quads. So if I take this and ask where is this greater than like 0.99999, it's going to isolate the space. So if I go here and then assign it to the selection, that's going to be added. And then, this one's going to be added. And then if I swap this out with the second, now you're going to see we have our second group where I can now select these 4 and assign it and whatever. And this is useful for a whole bunch of things, right? So if I wanted to have 2 principled BSDFs, one of them red, one of them white, I can use this as a mixing factor to make different materials without adding a bunch of material slots. So that's useful. You can make all kinds of different selections. Speaking of attributes and stuff like that, I said that you can pull attributes from basically anywhere in Blender, and one of the most powerful places to do this is you can pull from geometry nodes, which is a place where you can actually assign attributes. So here I have a very subdivided plane, and what I want to do is I want to make a special kind of attribute that highlights a certain letter, like the letter A. This is something that basically be impossible to do with shader nodes, at least in a simple way. So I'm going to type out A as my string, and then I'm going to use a string to curves node. So what I'm doing over here is I'm basically just making the geometry of this, which we are soon going to make an attribute. I do want this to be centered. You're going to see that this is a curve instance. That is important because if I want this to be geometry, I have to realize it. So now this is actual geometry data. And what I want to do is I want to say, grid, look at that letter and tell me where you're close to it. The way you do this is you use a geometry proximity node. As you expect, you can't just use a curve here. So I'm going to set this 2 points. I don't think you can use a curve here. Either way, we want this geometry proximity because it tells us the distance. So let's actually view this distance with this grid. You're going to see we get an error because like I said, this is a curve. So I'm just going to make it a mesh. And then all of a sudden, you can see we have this data of distance inside of our grid. And even more so, if I set this to edge, now we have it's not yet an attribute, but we have the data of where it's close to the letter A. I can take this information and make it an attribute. So I'm going to call this attribute literally the letter A, and I'm just going to connect this here. But now if I set a certain material, so I'm just going to make the material, and then I go into this, I can again use this attribute node, make the name the letter A, and then change the factor. And now you can see we have the letter A that we can do whatever we want with inside of shading. I changed the string from the letter A to the letter B. It's going to update because this attribute is changing and then shipping over to the shader node. And now I have this cool animation that I can swap out the letter to E or, whatever you want it to be. You could even type in many letters as long as they fit After Effects. My voice is gone. How many more? 3 more. Actually, not 3 more because we did do circles, squares, and squircles. Okay, 2 more. For this one, I want to talk about a node I feel like I didn't even know about. Like nobody uses it, and it is the point density node. This is because it doesn't really have obvious use cases. When I view point density, whether it be the color or the density, you're not going to see anything. That's for 2 reasons. reasons. The first reason is we didn't pick settings, and the second reason, this density is called that because it's actually a volume metric, okay? So you don't even put it in the surface. So point density is basically going to give us a volume, at least the density data for a volume, that looks at either a particle system or the vertices of an object. This is great because these object vertices can come from any object, not necessarily itself. But I'm going to select itself as the object that we care about the vertices of. I'm going to change space to world space so it works wherever I move it. You're going to see it makes a volumetric. We don't necessarily know what's going on here, but as I take this radius and make it tiny, you can kind of get a hint. I'm going to bump up my resolution so it's a bit sharper. So what you're going to see is kind of like these like hemispheres or spheres or whatever, and those exactly correspond to, let's turn off proportional editing, those exactly correspond to these vertices. And by the way, if you're seeing like I did the dragging and it doesn't necessarily update, right? Like it is updating, but it doesn't go all the way up to the vertex. I think that's because you need to do a refresh. And yeah, now you can see the volumetrics here. So another reason point density is very awkward, but remember, we can use any object here. So I'm actually going to put a cube inside of this Suzanne, and then I'm going to say, actually look at the cube. And then I'm just going to bring up the radius so it's more visible. And you're going to see our cube that is hidden inside of here. Let's actually reveal it and then move it around. It's going to look at the vertices out. Instead of a vertex color, let's look at the vertex normal, which this is a three-dimensional, in other words, a vector or color quantity. So I need to change the color. And this is going to give us our points, but also the direction that they're facing. So if I now take this and I subdivide it, so now this has extra geometry, I'm going to refresh, and now I get all of these points inside of here. So you can use this for all kinds of like weird visualization. Again, this works with a particle system. I'm not going to do that here because I don't really know the use cases quite yet, but they do exist, and this is cool. And then finally, we have the biggest trick of them all, which is how do you take like nothing, no lights, no objects, nothing in your Blender scene and actually render something? Well, the answer to that is yes. And before I do that, I'm going to take this film and make it not transparent so we can see what is an HDRI in this case. And this is going to give us a big hint as to what we're doing. Because we have no geometry yet, we can see this like HDRI. So I'm going to delete this, and I'm going to use our final coordinate system of the day, which is not this, but windowed coordinates. They look very similar to UV coordinates, and in a sense, they're almost the same thing. So you can see we have black down here, and as we go on the X, it gets brighter on the red and then brighter on the green if we're mapping to the window. So as I shrink this, it responds to this UI. And just like before, I can do all kinds of like calculations. So I can take the distance from, let's say, 0.5 and then view that. And now we have this like black circle here. It's an oval because, again, it respects the window resolution, or I guess the aspect ratio, less than a certain number, and create these circles. Or I can use windowed coordinates to create like a wave texture maybe. And you can do all kinds of things. It doesn't matter where you're looking because, again, it's just using windowed UV space. So I don't know. I don't want to talk about it anymore, but those are the tips. You better appreciate this because I've lost my voice. 21 tips, maybe 20, maybe 22. I didn't count them. Okay, bye.